Now, in this example, I'm not actually going to work all of this out. Like, there's a bit of a grind to writing all this out, and I want to try to keep this video short. The thing I want you to see with this is that lower sum and upper sum is actually called by something else, depending upon which textbook you're looking at, but doing the left and the right endpoints. So rather than asking for a lower sum or an upper sum, oftentimes you'll be asked to figure out, approximate it using right endpoints or left endpoints. And that means that you can see on this one, ooh, that's an eraser, not a pen. So you can see on this one that all of our endpoints, let me make this big, all of our endpoints, bigger, bigger, yeah. All of our endpoints are on the left-hand side of our rectangles. Meanwhile, on this one, all of our endpoints are on the right-hand side of our triangles. Rectangles. Now, note that it's not always going to be true that the lower sum is going to be the right endpoints and the left endpoints is going to be the upper sum. Depending upon the concavity of your function, it's going to change who is, whether it's a lower estimate or an upper estimate. More about which one that is. But just note that sometimes they'll ask for lower or upper sums, so then you need to look at how that curve is shaped. Sometimes they'll ask for left and right endpoints, so then you just want to make sure that either your left endpoint or your right endpoint of the rectangle is on that curve. Now, with all of these rectangles, oftentimes you're like, well, is there a way that we could kind of like split the difference? Because sometimes we get vastly different answers depending upon if we use the left or the right endpoint. Well, could we kind of go somewhere in the middle? So, yeah, there's the midpoint rule. So, rather than having those rectangles, the corners of them being on the left or the right, what if we had it line up right in the middle? That might get us a better estimate for where the actual area is going to be. So if we looked at this curve, they want us to have 4 chunks. Oh, that's really big. Okay, they want us to have 4 chunks. So we're going from 0 to 4. So this is our start, and there's our end, and they want us to have 4 rectangles. So that would make 2 rectangles, and then this would make 4 rectangles. But where they want our values to be, so if we figure out the area is going to be approximately, the width of our rectangles is 1/2. But we don't want to use, for this first rectangle, we don't want to use 0 or 1/2. Nope, that's 1, sorry. We don't want to use 0 or 1 because if we used 0, that would be a left-hand rectangle. If we used 1, that would be a right-hand rectangle. They want us to do a midpoint. So in between 0 and 1 is 1/2, which is right here. So we're going to make our first rectangle use the height of 1/2. So we'll have to find f of 1/2. Then we got to do this one. So it should be in between these two. So again, we don't want to use 1 or 2 because that would be left or right. Oh no, don't save. Yeah, everything's fine. Everything's fine. It's fine. We're all fine here. All right, so in between 1 and 2 is 3/2. So that'll be plus f of 3/2. Then we want this spot right here to be our next rectangle. So you can see how the rectangle, like we are still missing stuff here, and we get a little bit of stuff that we're including that we shouldn't. So the two might kind of like even out a little bit. We can get a better estimate. So this is f of, let's see, 2.5, so that's 5/2. And then finally, here's our midpoint between these two values. So then there's our final rectangle. So plus f of, you can see the pattern here, 7/2. Area is approximately 1/2. By the way, all these are being multiplied by 1/2. Now it's just a matter of plugging 1/2 into there, 3/2 into there, 5/2, whoop, 5/2 into there, and then 7/2 into there. I'm going to cheat because there's no reason to like spend a lot of time like calculating all those. So f of 1/2 is 2.25 plus 8.25 plus 16.25. I did this before, so I'm just cheating. Plus 26.25. So this tells us when you calculate all that out, the area is approximately 53. Now, Finney, this really threw me off when I first was learning this. This, like the LRAM and RRAM and MRAM, like it's really was tricky for me to find. So I want to make sure that you know that RAM is just saying the rectangular approximation method, which is what we have been doing in this video, making rectangles to approximate the area underneath a curve. The LRAM is saying that we're looking for the left-hand rectangular approximation method, that the left-hand side of our rectangle is touching the curve. The RRAM means that the right-hand side of our rectangle is touching the curve. And then finally, MRAM is saying that the midpoint is what is right on our curve. So it's just saying that's just their notation for it, but they almost never say what that means. So I wanted to make sure that you know what LRAM, RRAM, and MRAM mean, because boy, did that drive me crazy. All right. So we're taking a look at some bottle bobbing around the stream because we have an hour to just watch a bottle float around the river. But we want to figure out how far the bottle travels upstream during that hour. In order to find it, they're asking us to do LRAM and RRAM. Well, why is that? Well, if we're looking at velocity, velocity is the derivative of a position function. So it sure seems like this rectangular approximation thing is antiderivative. Ooh. But we're not, we're going to deal with that later. But for now, let's just say, hey, guess what? LRAM, RRAM, that's going to tell us how far it has traveled during that time. If we want to do LRAM, so that's the left-hand rectangular approximation method, that means we want to make sure that our left-hand side is on the left-hand side of the rectangle is on our function. So that means the numbers that we're going to use for the LRAM, we're going to use all these and all these, but we won't use the last one. When we go after RRAM, we're going to use all these and all these, but we won't use the first one. Now, note something sneaky about this one is this is in minutes and this is in meters per second, and we need that to be consistent. So we're going to say 5 minutes, just, well, we're not going to say it. It's very true. 5 minutes equals 300 seconds. So when we work on this problem, I can't spell 300 seconds for some reason. The width of each one of our each one of our rectangles is 300. So rather than saying that the width is 5 for each rectangle, we need to say that the width is 300 so that everything is in terms of seconds. We could do everything in terms of minutes, but I don't really want to convert all those minutes per second into meters per second into minutes per second. That'd be silly. So the LRAM is going to be the left-hand approximation. So I want to use all of these values and all of these values, but I will not use the last one. Now note I've kind of skipped over it. 12 sub intervals. We do have 12 because we've got 60 minutes. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So it is 1 plus 1.2 plus 1.7 plus dot, 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 dot. You just want to do all of these and all of these, but not the final one. Doesn't really matter because it's 0. So the left-hand approximation, let me just cheat because there's no reason to watch me type stuff into the calculator, is going to be 300 times 17.4, 5,220. So this is the number of meters it has traveled according to the left-hand rectangular approximation method. We do RRAM. That's going to be 300 times, we want to do all of these and all of those. So we have to skip the first one. So we're going to go 1.2 plus 1.7 plus 2 plus blah, blah, blah. So that is 300 times, it turns out to be 16.4. Because again, you got better things to do than watch me type numbers into a calculator. 4,920. So that means after that hour, according to the right-hand rectangular approximation, the bottle has traveled 4,920 meters. Done. So to wrap up our rectangular approximations, RRAM is the rectangular approximation method. Most of the time, you're going to be asked to do either a left hand or a right hand or a midpoint rectangular approximation. And the Finney book likes to abbreviate it as LRAM, RRAM, and MRAM. With these, we're not trying to get a perfect area. We're just trying to get an estimate using a bunch of these rectangles. And we didn't use a lot of rectangles today. But what if you use more? Like a lot more. Like a lot more. That's going to be coming soon. So thanks for watching. Have a good day.